Okay, let's suppose we are trying to get a solution due to this sine excitation. Okay, then what y would look like? Y can be sine or cosine because we have y dot, right? Assume that y equals sine, then this is cosine and this is a sine. That means even if we put the sine over here, the response would be sine and cosine, or I say sine omega t plus some phase. Okay? So it's not convenient. So somebody say that, okay, then why don't I say I am exciting with complex function y exponential j omega t. And say, if I want to take only the response due to sine excitation, then why don't I say real part? No, imaginary part of the excitation I am doing. Then I just take the response imaginary part over here. That's okay, right? Because this is linear system. By doing this, I don't have to worry about the sine, cosine, sine, phase, everything. Right? So that's why we like to use complex notation. And what we do is using complex notation, and the complex notation essentially provides us the relation between magnitude and phase. Okay? That's why we are using complex notation for convenience. So use this, and we have this result. So let's draw the result in real and imaginary axis. Okay. Say this is real axis, this is imaginary axis. Okay. And the excitation is f exponential j omega t. Okay. How do I draw it? Okay, this is f. Okay. That f has real part and imaginary part. Okay. And then minus j omega t means it is rotating in this direction or this direction. Which direction? This direction. Right? So expressing f exponential minus j omega t in complex domain is rather interesting. I have complex amplitude and this is rotating. And if I want to take the real part, I only take the projection of complex amplitude to the real axis, vice versa. Okay, so that is f. And what is c? What is sy? Sy is, y is also complex, and I assume that y is this magnitude, and the cy, sy is like this, sy. Okay, and what is then minus j omega r y? What I have to do is I multiply omega over here, And then minus j means that I'm rotating this way, this way, this way. Okay, j is exponential j pi over 2. So that is rotating this way. So minus j, I'm rotating this way. So I have to go this way. And that is minus j omega r y. Okay? And also, I have omega square m, that is multiplying minus j omega over here, and the scale with m, right? So that is another 9 degree over here. And the summing this has to be same as f. Okay? So what I will do is, okay, this is the force acting on spring, and I move this one over here. This one over here, it looks like this. And I move this one over here, that looks like this, right? That has to be same as F, so F should be over here, right? So, summarize, this is called the phasor diagram. Okay, this is real part, imaginary part, and I have y, sy, and I have minus j omega r y, and I have minus omega square my, and this has to be same as f. Okay? I draw this equation in complex plane. That's what I did. And this is the phase difference between force and displacement. Right? That is the phase difference between force and displacement.